Well, hello everyone. We are team number 22071, and this is the LifeGrow Bot. The LG Bot is a modular, autonomous vertical farm unit designed for use in an indoor plant production facility. My name is Chris Kaufman. I'm the project lead and a biosystems engineer major.
My name is Tristan Martin, and I'm the procurement lead majoring in biosystems engineering.
I am Joseph Green, and I am the mechanical lead majoring in mechanical engineering.
Hi, my name's Tom Maylard. I'm a mechanical engineering major and a structural designer for this project.
My name is Diego Moscoso. I am the computer lead majoring in electrical and computer engineering.
By the year 2050, we are expected to reach a global population of around 10 billion people. With this large of a population, traditional agriculture is struggling to sustainably keep up with the demand. Now, controlled environment agriculture has helped mitigate much of this, as methods such as indoor vertical farming have allowed for a higher yield of crop in a smaller footprint. The main issue with vertical farming is currently the high labor costs. With that, we'd like to introduce the LifeGrow Bot. The LG Bot is a concept patented by Dr. Joel Coelho with the intent of automating vertical farm production based upon existing warehouse robots. The LG Bot is a modular autonomous robot with a hydroponic growth unit mount. It is intended to work in conjunction with a cyclical production process such as the automated circular operational protocol, which is also patented by Dr. Coelho. As the crops grow, the LG bots will move to their particular growth room. This process allows for no people to be involved in the crop production. Here you can see the system requirements agreed upon by the sponsor and the team. Adequate power to all the components was a critical requirement, as was the automation. These are two of the most important design features and were the first and second critical design elements of the project. The weight-bearing capacity was also a major focus, which required quite a bit of modeling and testing. Although the LG Bot is intended to operate in a facility without humans, safety features were included. Of course, uniform and successful crop growth was a necessity. For each requirement, we conducted either a test, an analysis, a demonstration, or an inspection. The LifeGrow Bot is a 3-tiered hydroponic system with the capability of growing a total of 72 leafy green crops. The base of the LG Bot contains the Raspberry Pi microcontroller, which manages the autonomous movement of the unit. Stepper motors and omnidirectional wheels allow for precise movements to and from the charging station. The structure of the LG Bot has undergone many changes through the course of its development, with one of the major ones being the fact that the team settled on an all-in-one unit rather than a mover bot in a separate growth tower.
For our structural component of the robot, we needed all material to be both strong, lightweight, corrosion-resistant, machinable, and able to be welded easily. For this, I chose the 6061 and 63 aluminum. I used the 6063 square tubes for the body of the robot, cutting 3 feet, 4 feet, and 6 feet sections, then measured out and drilled 3/8 holes in order to connect them all together using galvanized bolts. We chose 3/8 as our standard bolt since we were sure that these bolts would be able to take the load imposed on them. I used galvanized bolts, nuts, and washers to help fight corrosion. The structure looks almost one-to-one what we modeled in SolidWorks because of this, from the placement of the different square tubes to the perching rods. The structure is created in a way that the robot will be bottom heavy and will therefore not have an issue with tipping even before the batteries and water tank are placed. This is one of our safety features.
The LifeGrow Bot uses Mechanim Omni wheels in order to displace itself in directions unaligned with its position, allowing for a much greater form of maneuverability. Here in this video, the Mechanim wheels are shown to move as planned, with opposite wheels having opposite rotation and reaction forces depending on the desired direction of movement. This allows for multiple drive directions where we can obtain back, forth, and sideways motion, all without having to rotate the craft itself. The drive system consists essentially of a motor, chain and sprocket, and wheel. The motor sits on the bottom of the shelf and the axle is supported underneath. They are then connected by a chain and sprocket. A specific sprocket ratio was chosen based on the motor torque output and what torque was needed to be outputted for each wheel. These values were determined via system force and torque analysis. As you can see, the frame is more than able to withhold the weight planned for. This shows that sufficient margins were used in the calculations and accounted for. For the final design, the LifeGrow Bot essentially consists of an autonomized, heavy-duty, and maneuverable structure capable of sustaining a hydroponic growing system.
The motors, drivers, and Raspberry Pi are all powered by a 24-volt, 20-amp-hour battery, which are charged when the LG Bot docks to its station. A Vail 50-amp, 60-volt copper charging contact set was used for the docking station, which is wired to a 24-volt, 20-amp smart lithium battery charger. As a safety feature, the charge plates were mounted toward the top of the bot to reduce likelihood of human contact, although a relatively low voltage is running through them. The LG Bot utilizes a 120-volt AC sine wave inverter to power the hydroponic pump and the sand and bio lights. Due to the high power draw of these components, the hydroponic parts only operate whilst the bot is attached to the docking station, as a relay is used to trigger its operation. Here you can see the full electrical analysis of these components, as several tests and inspections were performed to verify that not only the hydroponic components would be able to operate continuously, but the batteries would always have sufficient charge for powering the motors and microcontroller. All electrical components come with safety features to prevent overcharging or short-circuiting. The Raspberry Pi 3 Model B Plus single board computer was chosen to drive the system due to its compute power and high number of GPIO pins. These pins enable use of the motor drivers and the LiDAR, ultrasonic, and camera sensor array. The LiDAR sensors guide forward and backwards movement, while ultrasonic sensors assist in close-range side-to-side guidance, specifically for charging. The compute power is required to carry out the two-step navigation system of 1. Global path planning, which constructs the route to follow, and 2. Local navigation, which moves the system and modifies the path according to real-time sensor data. A graphical user interface was also created to give users access to the live-streamed camera feed. This GUI also gives access to start, stop, and charge functions, which begin movement to a subsequent waypoint, stop movement and all other ongoing processes, and move the entire system to its charger, respectively. To verify automated navigation, an OmniWheel robot kit was purchased to test the software. The robot was instructed to move to 4 different waypoints at 3, 5, and 8 feet away from its starting position. These results were initially promising using DC motors. Thus, this test was repeated using stepper motors for the final build with larger distances. A form of this verification test will be on display for design day with a decreased traversal speed and increased software-defined space needed by the system to safely move.
Last but not least, we turn to the hydroponic system. The LG bot utilizes a nutrient film technique, which pumps a thin recirculating stream of water to irrigate the crops. A 15-gallon reservoir was deemed suitable for the 12 NFT channels used in the design based on some simple flow calculations. An 800-gallon-per-hour pump was in size based upon the calculations shown, compensating for a 30% efficiency loss over time. For each level, there are 3 Sanan Bio lights, which are mounted to the frame using a custom 3D printed part. These lights have an optimized spectrum for the growth of leafy green crops. By using PVC pipes and specialized 4-inch Crop King channels, a total of 72 plants can be grown while maintaining easy access for harvest.
Following the traditional systems engineering approach, we agreed with our sponsor to deliver 4 review presentations as well as accompanying documents such as the technical data packages and SolidWorks drawings. The 3 biggest lessons we learned were 1. Underestimating the initial power demand provided by the charge controller, leading us to purchase a new higher voltage charger. 2. To increase the torque of the motors, we first planned to use 3D printed gears, but after multiple tests, we changed to an alternative chain and sprocket gear system. 3. In regards to the autonomous navigation system, additional sensors for each side, as well as a camera object recognition, would increase precision of the system's movement. Wireless communication would also increase precision between multiple LG bots to path plan together.
The LifeGrowBot team would like to thank the following people for their contribution to this project. Without their help, we would not have been able to meet our design requirements.